I will focus on the idea of the punch facade as a building performance tool. And by that, I really mean when I talk about building performance, that is in the idea of the energy management, whether it be in the embodied carbon that goes into its construction and or the ongoing energy consumption to heat and cool it and create comfort, thermal comfort within the building. And I like starting with the idea of a punch facade because it really kind of shifts the way we might typically think about curtain wall systems. It would be very easy to think about glass curtain wall systems as or curtain wall systems as glass, where we add things to create opacity or visual interest to it. When we talked about a punch facade, we're starting with an opaque wall surface. And what's really important about that is once a wall surface is opaque, it can have high insulating value to it. Glass transfers heat very readily. And so the idea of seeing this glass half empty or more half full than half empty, we start with a large wall surface and we try to make as small of openings as possible in order to balance the requirements for creating good views, connections to the exterior environment with the idea of energy efficiency. And that's just a control through the whole spectrum. We can have something that's 80% glass, we could have something that's 20% glass, and we could actually modulate that throughout the whole construction of the building while continuing to have a kind of a continuum of design intent and materiality. So punch facades, I think, is a great place for us to focus on this idea of energy usage. So I kind of want to describe that idea about that relationship between solid wall and window. So if we looked at 100 square feet of anything, like a window, 100 square feet of window area loses at a 30-degree temperature differential with standard kinds of double pane thermal window construction, let's say 930 BTUs per hour. An easily high insulating wall today could be an R30, and it could be losing only 100 BTUs per hour. So significantly less energy being transferred. And this is also related to not only heat when we're talking about heating and cooling, losing heat to the external environment, but the window is also a net energy gain during solar insolation. So it can be in many climates, the amount of energy that it emits, solar gain, has to be dealt with air conditioning. So their window systems are very problematic in their ability to freely move energy between two spaces, as opposed to opaque surfaces. And you know, some ways I'm making some generalizations here to just get us started on this thinking. So if you think about now mixing those two together, which is what the punched wall is, we now have, let's say, a 50-50 mix of window and solid massing. And now we've taken that, what would have been a glass wall at 930 BTUs, and reduced that to 515 BTUs per hour. So we really made a significant reduction in the amount of consumption over an all glass window. And obviously, there are downsides to that. It's beautiful to have all glass, but in many cases, we can't have all glass. We need privacy. We have to worry about solar overheating. So this could be a nice balance. And if we're really looking at getting to high performance buildings, we can actually reduce that glazing area even more and really start to reduce it. So when we go to 3/4 of wall area to 1/4 of window area, we're really down around 370 BTUs per hour. And those are just random numbers, but what we've done is by going to that window, by reducing that window area to 25%, we have more than a third reduced our energy demand by more than 2/3. So it's a really significant contribution to performance. And I say that because there's always, it's just a way to start thinking about it. None of this is, there can be all kinds of arguments on both sides about the way I'm doing this analysis. And I'd like to point out one of those is that advances in what we do with glass are going to change that kind of analysis. And so, for instance, I have, this has really just come in the market in the last few years. The idea has been around forever, but the idea is that if you take two pieces of glass and you bring them, you know, with an air gap, like an insulated unit, but even closer than that, very close to each other, but still with air between them, you can evacuate all of that air and create a vacuum between those two glass panels. And when you do, you're really creating a wall that performs like a thermos bottle. And the R value can go then from, you know, maybe an R1 to an R15, which means it can start to, like as you see in that illustration over my head, if you combine that with some a vacuum insulated glass panel with another piece of glass in a conventional um, insulated glass construction, you can approach R values of R16. So that's really where we might go in the future. The reason they're able to accomplish this is because they can draw that vacuum. If you were to draw a vacuum on two pieces of glass that are very close together, what they would actually do is fracture. When you evacuated all the air, they would bend so much as to collapse in on each other, or they would just physically make contact with each other, and that would reduce any kind of insulating properties because now we would have just direct thermal conduction. So what they do in order to do that, in order to create that, break that ability of the glass panes to touch, is they insert these little micro supports, little plastic standoffs, not unlike what you would find if you had a cardboard, if you ordered a pizza and it had one of those little plastic stools that prevent the cardboard from touching the top of the pizza. You can imagine these on a really small scale between the panes of glass to prevent those glass panels from touching each other. And that allows you to draw that vacuum. And they don't really have much of a visual appearance because they are so small. Um, the problems with this right now are that these need to be evacuated at a very high level. They, their longevity, how long they last, when the vacuum needs to be replenished or dealt with, whether they need to actively be managed. These are all things that are out for speculation right now, and they may have very high cost to them. So it is in the future, though, just to review, that what I'm talking about in the window wall mix, that R value of 3.2 could go to R19. Remember also, though, that this has a cost to it, a capital cost. So if you're investing money, that money has a footprint to it. So it may still be a balance with using older technology well into the future before we get to these kind of high performance window systems. I want to preface this whole discussion about this punched opening because this is actually this will be our fourth experiment. We looked at the initial introduction of rain screen panel. We introduced variations in curtain wall, and we finished with something that looks like this 10 Bond Street that I'm showing you. And then we experimented with hanging systems of modular curtain wall systems. And this is really kind of going to become the kind of final point in this course about our kind of examination of the performance of facades. And it is actually in preparation. The work that I've done, I presented at a conference, though, with Facade Tectonics World Congress, and I'm going to do that again this year. And really, our previous work has been some of the subject of what a research paper has been. And I'm really hoping that we're going to participate here going forward in actually the kind of culmination of what this research paper will be. And that's your experimentation with developing your own kind of punch facade systems with regard to increasing building performance while maintaining, or maybe primarily to you, while creating interesting and engaging facade systems. Next, we'll cover the kind of materials that would be involved in these kind of facade systems.